Okay, now we're going to talk about reversibility. Reversibility is the key to the second law of thermo. A reversible process is one that's perfectly efficient, has no friction, no dissipation whatsoever. Entropy and the Carnot efficiency we'll talk about, and the second law of thermo. Introducing the second law. Reversible processes. They occur without a driving force. So if there's no driving force to push something one way or the other, it could go one way or the other, and hence we call it reversible. They barely happen because there's nothing to push it one way or the other, so they barely happen, and often these are referred to as quasi-static processes. Static meaning not moving, and that's what a reversible process would have to be to occur. It's really an idealization. Let's take, for instance, heat transfer. Heat transfer depends on a heat transfer coefficient. We call that U, overall heat transfer coefficient. The amount of surface area available for heat transfer, and you see heat transfer devices usually have a lot of surface area, and a driving force, a temperature difference from one side to the other. So heat always flows downhill spontaneously. So you need that driving force to make the heat flow. However, the more the driving force, the more the gradient or the difference in temperature from one side to the other, the more inefficient the process will be. And so we never have truly reversible heat transfer. There always has to be some temperature difference to make it flow. If the driving force is zero, we get the most efficient heat transfer. Again, saying the same thing, but also the very slowest. As delta T approaches zero, there is virtually, let's say, stopped heat transfer, quasi-static. Quasi meaning sort of, and static meaning stopped. So reversible and efficient, those concepts go together. So again, as engineers, we're trying to balance the inefficiency of high gradients or high driving forces with the need to make things happen in time. So a reversible process is very efficient but also very slow, and it never happens. Alright, remember heat flows downhill, and oh gosh, I've got my delta T upside down, but you can see it's reversible if delta T approaches zero. So I'll go from a hot space to a warm space, but only if there is some driving force to make that happen. Okay, recall our piston. Here's another look at gradients. We have an external pressure and an internal pressure. If the external pressure is greater, then it'll push down the piston. But the work is more efficient if we make those external pressure. We'll call that the load. Suppose the internal pressure is higher and we're trying to push the piston up. So we'll need the internal pressure to be slightly higher. But if we lubricate the edges of the wall of the cylinder, then the piston will slide very easily, and the internal pressure of the gas, let's say, can be balanced by the external pressure of the piston. If that's the case, then we have close to reversibility. It always has to be some difference to move, but as you reduce the friction, reduce the inefficiencies, you can get toward a reversible process or an almost reversible process and improve your efficiency. And we all know that lubricating the pistons will improve the efficiency. If there is friction, then some energy is dissipated. What happens to the energy? As the friction occurs with the wall, that energy that's lost, the friction, winds up heating up the gas or heating up the walls of the piston, but it usually turns into some sort of thermal energy from the friction, and that is a little harder to capture, actually quite a bit harder to capture that thermal energy and make use of it for power. In a turbine, we have the situation where we try to reduce the friction of the fluid itself. As the fluid comes through, spins around these blades, it's pushing the blades as it goes through the turbine. As it hits those blades, you want it to be hitting it smoothly, let's say, if it goes rushing past the blade with a different velocity, say here at the tip, than the tip of the blade, then you'll have friction created by the fluid itself acting against the blade or acting against itself, creating this friction which winds up dissipating into thermal energy that we really can't use. And for that purpose, in a turbine, as the gas expands, you'll see the blades are designed to expand so that they more closely match the velocity. As the gas expands, unless you allow for increased surface area or increased flow area, then the velocity will go up, and the velocity won't match the velocity of the blades, and you'll have problems. So that's part of your design, to try and make it closely match the velocity of the gas to the velocity of the turbine blade to reduce your friction. Again, here we have reversible if the gradient in velocity approaches 0. Okay, let's talk about the water wheel. And this is famous from the 1800s and before, when people were damming up streams using water to produce power. This is before the actual first, what we call, heat engine was constructed. We had water wheels, so water was poured into a bucket, and then the bucket would push the wheel down, and then as you got to the bottom, it would empty the water. And so what you tried to get was a match between the high space and the low space. And at that point, this distance here, the difference above the high space, if you put the water in up here and let it drain into the bucket, then what you've missed is this distance here between the temperature, there I go, rushing to temperature, between the height that the water came in and then the height that the water was actually accepted by the water wheel. If we could have put the first bucket up here, we would have had more potential, and again here we're talking about potential energy. Remember rho GH, that's the potential energy of the water here, rho GH, or let's say rho GZ. Down here's the potential here, so the ability to get the energy depends on its height difference. So the power that we produce is proportional to the flow of water times delta Z. And with this water wheel, we have delta Z as Z high minus Z low, but notice, could have gotten a little more because I missed some opportunity between this, let's say, top of the dam and where the water is actually received by the water wheel. Now I want to talk about the heat engine, which is analogous to the water wheel in many ways. In fact, the heat in, the heat coming out. Previously it was water coming in and water coming out. Here we have heat coming in and a different amount of heat going out. So we still have a flow, but it's a different kind of flow. Sadi Carnot, and we'll talk about the Carnot engine coming up. Sadi Carnot was famous for his development of the heat engine, and at the time, in the early 1800s, they had a concept called calorique. And you're going to see later that this is related to entropy. But I want to read something my advisor, Dr. Carlos Busat, wrote that is very inspiring, and he's actually the person that inspired me to study thermo. And so I want to read something that he's written recently about Carnot. A somewhat tragic misinterpretation of entropy was Sadi Carnot's calorique. Lazare Carnot and Sadi Carnot, father and sons, were engineering graduates of the École Polytechnique, one of the most outstanding research centers of the 19th century. Lazare had studied extensively the efficiency of mechanical engines, particularly water wheels. Sadi's studies took off where his father had progressed. A main concern of the water wheel was to reduce the wasted opportunity represented by gaps necessary to cause the water to flow in and out. Less power would be produced as the gaps increased at the entrance and exit. In spite of the success on defining the bounds for power, the answer to what happens to the lost power was left unanswered. Furthermore, the proper question was not even formulated until later. In his 1822 seminal paper, Sadi described an ideal heat engine known as the Carnot engine. It consisted of two reservoirs analogous to those needed for a water wheel, one at the hot source, TH, here we have T high, and another sink at the lower temperature, T low. A substance called caloric was transferred from hot to cold. We now know that heat is flowing in and out. A gas would be going around and around, again a la water wheel, transporting caloric from the high to the low reservoir. A piston or turbine would make use of the expansion of the heated gas and subsequent contraction of the cool gas to export power. The two most important conclusions of the performance of this idealized engine were, first, the maximum efficiency would be determined solely by the temperatures of the source and the sink. So here we have the source and the sink. And secondly, the efficiency bound was not dependent on the gas used to transport caloric. In addition to the two main conclusions presented above, Soddy addressed the sources of inefficiency in heat engines. As with water wheels, leaks to the surroundings were identified as trivial sources of inefficiency. However, a subtle source of inefficiency would be the equivalent of bypass or internal short-circuiting of the water flow. Thermal or short-circuiting is known as conduction. And Soddy's mistake was caloric was not a substance, nor a conserved entity, or a good representation of the thermal energy. He failed to see that the thermal energy discharged at TL would exceed the intake at TH. And again, we'll get to this later and we'll be able to prove these things. It took over 30 years and the genius of Rudolf Clausius to bring together the work of Clapeyron, Thomas, Lord Kelvin, Joule, and others, many of whom were rejected by peer review, to correct Carnot. In 1854, and this is some 30 years after Carnot, Clausius postulated that indeed thermal energy was not conserved, but combining heating and power was. He also proved that all real processes were irreversible and that entropy would always increase as a measure of irreversibility, the arrow of time. Engineers concentrated on the inefficiencies, and classical physicists seem to have had a fixation on equilibrium, both missing the point. In the universe, power is not lost, but is freely available for creative processes. I'll get that paper to you, and you can take a further look at it. Some really good details in there. But the point that we're making is that here you have, analogous to the water wheel, you have heat coming in, just as you had water coming in. And later we're going to find that's entropy coming in. But if you don't bring the heat in at the same temperature into the heat engine, like as we had with the water bucket, if it came in up here at a higher temperature, but was received by the heat engine at a lower temperature, you have some lost potential to do work between the high temperature that you bring it in and the high temperature that it's actually received. Similarly, when you're rejecting the heat, you have the low temperature here and an even lower temperature when you reject that heat out to the surroundings. So, importantly, we see that power is proportional to some heat flow times delta T, but it's really more like a Q over T, and we'll get to that later. Finally, we have, for a heat engine, and this was one of Carnot's conclusions, that the efficiency, we call this the thermal efficiency, the work produced, we talked about this earlier, divided by the heat that you spent to get that work, is proportional to the difference in high temperature to low temperature, as was the case with the water wheel, the difference from high elevation to low elevation. Now, it was observed that efficiency goes up with temperature, so ideally, as TH, and this was one of the things I just talked about, the high temperature and the low temperature are really what limits the efficiency of the device, not the fluid that's used in it. We find that as TH minus TL approaches TH, this proportionality constant for efficiency, remember it was proportional to the difference between T high and TL. This K turned out to be 1 over TH, and the efficiency then, TH minus TL over TH, or the well-known Carnot efficiency, the efficiency of a heat engine, the maximum efficiency of a heat engine, is 1 minus TL over TH. And that's widely used even today. Limits of any power-producing engine is limited by those temperatures. So let's look at the Carnot efficiency for an ideal. And remember, we call that reversible where there are no frictions. And remember, there can be no frictions only when there are no gradients. And we call that a reversible process. This comes out to 1 minus TL over TH. Now, solving Carnot's efficiency together with the energy balance, we can find some important things. One is that the efficiency, here we have work over QH in the top, because if you do the energy balance, you find that work is QH minus QL is equal to work divided by QH is 1 minus QL over QH. And for the Carnot engine, that's also equal to 1 minus TL over TH. We come to the result that QL over TL is equal to QH over TH. And this turns out to be, we're introducing this concept of entropy, this turns out to be a reversible flow of entropy. And so one thing I want you to remember is that heat carries entropy. So heat is carrying the entropy, and if it comes in reversibly, meaning if the QH came in at the TH and it was received by the process at the same temperature that it was rejected by the heat reservoir, then there is no gradient, and so we have a reversible flow of heat. Recall, that takes forever. And the idealization is reversible flow of heat. That is a reversible flow of entropy, and came to be the primary definition of an entropy flow. So Q over T evolved as a statement of entropy, and entropy which is conserved in an ideal process, but in the real world there are no ideal processes. There are no truly reversible processes. So you really can't say entropy itself is a conserved quantity. If it's ideal, if it's reversible, entropy in equals entropy out, or Qn over Tn equals Q out over T out. And as we move forward with this, we're going to find out that the imbalance of the entropy is always positive and always goes in the direction of advancing time, hence the term the arrow of time. So again, with an irreversible process, say we're heat leaking out of our house in the winter time, the Q will come from the inside of the house at TH. It will conduct through the walls, in which case you're losing that potential to do work, because as with a valve, if you put in work and you drop that pressure and get nothing for it, here we have TH leaking through the wall to TL, had the potential to go through some sort of heat engine and produce work. We did not use that, so we lost the opportunity to produce work, and that is an irreversible process. Since it's the same Q, different T's, it's obvious that Q over TH is not equal to Q over TL. So that imbalance is entropy. Now let's look at the general balance equation that we've talked about before. In plus generated equals out plus accumulated plus consumed. If we take it to be steady state, then in plus generated equals out plus consumed. And we've found that there is no entropy consumed. You've never found a process, there's never been a process where entropy was consumed or where we had a negative generation of entropy. All observed processes have always been S generated is greater than 0 and there is no consumption. In fact, to me, this is the most concise statement of the second law of thermo, and there are a lot of statements. To me, this is the one I use as an engineer. S generated is greater than 0, and in fact, the larger the gradient in the process, the larger S generated is going to be, as we'll show later on. We won't show it, but we'll show some examples of it. S generated, a function of the gradient. Second law of thermodynamics, S generated by every process is greater than or equal to 0. Second law puts a limit on the process, and that is, if S generated equals 0, that's the best you're ever going to do. That's the best you're going to ever do. You have what's called a reversible process. In order for S generated equal to 0, you can have no gradients, which tells you the process will never happen. It will take forever. In a practical sense, you wind up with very, very large equipment, very, very large heat exchangers to force that delta T down to 0 or delta whatever down to 0. And so we have no driving force for flow. The flow never happens. We have a quasi-static process, a reversible process, basically one that never happens in the real world. Still, it's an idealization and a limit on what we can do. So the second law, the entropy balance, is used to, 1, determine the best outcome if we have a reversible process, or 2, quantify how irreversible the process is. So if I calculate S generated for one process, I can compare it to the S generated for another process, and I can say, well, this one is more irreversible than this one. Example. Heat is to be provided at a house at 70 degrees when the outside temperature is 30 degrees. If the house loses 5 kilowatts of heat, what's the minimum power required to heat the house? Now the key word here is minimum. And when you're thinking about the second law, the law of irreversibility and entropy, you think, well, minimum, what's that mean? If I'm looking for the minimum, that's often the best I can do. In this case, it's the best I can do because I'm using power. So that's going to imply that I have a reversible process. So in my entropy balance, when I have a reversible process, I set S generated equal to 0 and go on about my balancing. Here's the example. I have heat moving out to the outside from the house, and I have to replace that heat. My heat loss is 5 kilowatts. So I'm going to replace that 5 kilowatts that I lost with a heat pump, put a heat pump on the house, and tells me that that QH here has to be equal to 5. So now I have to find out how much work I need to put in, and remember, we're looking for the minimum work, and of course there'll be some QL that has to be drawn from the outside to be added to that work to replace that 5 kilowatts to the house. Otherwise the house will cool down. Energy balance on the heat pump. The work in plus the heat in equals the heat out equals 5. That's how much we need. The entropy balance becomes QL over TL. Remember, we're defining entropy as Q over T. So here we have the QL over T. Supposing we can get it into the heat pump at the exact temperature of the surroundings, the cold surroundings, plus the S generated equals QH over TH. And again, that QH is going from the heat pump to the house at the same temperature of the house. No gradients there. S generated, because we're looking for the best we can do, the minimum, we'll set that equal to 0. Plug in the calculations and you find that we only need 0.38 kilowatts. So for 0.38 kilowatts of power in the very best engine, and we'll call this a Carnot heat pump, the very best we can do, we only need 0.38 kilowatts of power, and we get 5 kilowatts of heat into the house. Now that's a heck of a lot better than plugging in a space heater, in which case you get 1 unit of power and 1 unit of heat. So, using the best heat pump we could ever build, which by the way would be a massive device, the work power is only 0.38 kilowatts. Using a strip heater, the work would be 5 kilowatts. You get 1 for 1. If you plug in a strip heater, you're wasting energy. You plug in a strip heater, you're getting heat, work directly into heat, very inefficient. So that was the combined first and second law, energy balance with the entropy balance. As engineers, we're using this all the time to solve problems. Powerful combination using those two balances. So we talked about reversibility, where we're using processes with a low driving force to approach reversibility. And remember, reversible processes are slow. In fact, they're almost not even moving. That's what makes them reversible. And we talked about entropy and the Carnot efficiency, and that Carnot observed the basis for entropy from heat engine data. Actually, as we just learned, Carnot had the sort of the precursor for entropy, and it was Clausius later on that came and pulled it all together and devised this concept that we call entropy. The concept of entropy evolved to describe the irreversible nature of real processes, and in fact, that is the arrow of time. The direction that time moves is always in irreversible processes. Now, I always like to have you imagine how funny it would be to turn the clock back and rewind a video, and then you can see what an irreversible process is. If you play a video backwards and it looks just like it would going forwards, then that might be what I'd call an irreversible process. Say you have a perfectly elastic ball and you drop it on the floor, it comes right back up to the same height. Take a video of that and you'll see the ball dropping. Let me draw it with my little laser pointer. It bumps up like this, say this high, bumps this high, this high. But in real world it bumps this high, and then this high, and this high, and this high. It's losing energy at every step. It's dissipating energy into the ground, into the ball. Heat is being lost. But if you played it backwards, that ball would be getting taller with every bounce, and you'd say, wait a second, that's not right. So if you say that's not right, playing the movie backwards, then you've got a true irreversible process. So that's kind of the link between entropy and time. So the second law, entropy is generated by real processes. Entropy generated quantifies irreversibility. And zero entropy generation is an idealization, and we can use it to determine what the limit on the best we can do is. So for your homework, what I want you to do is look through Chapter 6, and there are a lot of little problems back there. I suggest you work the ones with answers so you get some feedback. I'll also post some things on our website or on your Blackboard account. And work through the examples in this module and the problems in Chapter 6, and that should get you some working knowledge of these concepts.